Displacement, velocity, and acceleration in piping vibration analysis, fundamental measurements for understanding dynamic system behavior. Introduction to vibration parameters, displacement, velocity, and acceleration. Vibration in mechanical systems can be quantified using three primary parameters: displacement, velocity, and acceleration. Each of these parameters represents a different aspect of the oscillatory motion and behaves differently across the frequency spectrum. Displacement measures the physical movement of a component from its equilibrium position, which is most pronounced at low frequencies. Velocity, on the other hand, provides a balanced representation across a wide range of frequencies and is directly related to dynamic stress, making it the most practical metric for assessing vibration severity. Acceleration emphasizes high-frequency components and is particularly useful for diagnosing issues such as acoustic excitation or structural resonance at elevated frequencies. Understanding these parameters and their frequency-dependent characteristics is essential for engineers to select the appropriate measurement technique for monitoring and troubleshooting vibration-related problems. This knowledge ensures accurate interpretation of vibration data and helps in implementing effective corrective actions to maintain system integrity and reliability. Displacement characteristics, behavior, and limitations of displacement. Displacement refers to the distance a vibrating component moves from its equilibrium position during oscillation. At low frequencies, displacement amplitudes are relatively large, making it easier to observe visually. However, as frequency increases, displacement decreases significantly for the same energy input, rendering visual observation unreliable for assessing vibration severity. This limitation is critical because engineers often assume that visible movement correlates with high stress, which is not always the case. Displacement measurements are useful for detecting low-frequency issues such as structural flexibility or loosened supports, but they fail to capture the dynamic stresses that occur at higher frequencies. Consequently, relying solely on displacement can lead to underestimating the risk of fatigue failures in components subjected to high-frequency vibrations. For comprehensive vibration analysis, displacement should be considered alongside velocity and acceleration to provide a complete picture of system behavior. Velocity as a key indicator, advantages and relevance of velocity measurement. Velocity is widely regarded as the most effective parameter for vibration monitoring because it offers uniform weighting across the frequency spectrum. Unlike displacement, which dominates at low frequencies, and acceleration, which emphasizes high frequencies, velocity provides a balanced representation of vibration energy. This characteristic makes velocity directly correlated with dynamic stress levels in components, enabling engineers to assess fatigue risk accurately. Velocity measurements are particularly valuable in industrial applications where piping systems, rotating machinery, and structural components are exposed to varying excitation sources. By using velocity as the primary metric, maintenance teams can prioritize corrective actions based on actual stress conditions rather than visual cues or isolated high-frequency readings. Furthermore, velocity-based criteria are standardized in many industry guidelines, reinforcing its role as the preferred method for evaluating vibration severity and ensuring long-term reliability of mechanical systems. Acceleration and high-frequency diagnostics, characteristics and applications of acceleration. Acceleration measures the rate of change of velocity and is highly sensitive to high-frequency vibrations. This parameter is essential for detecting issues such as acoustic excitation, resonance in thin-walled components, and localized structural anomalies. At elevated frequencies, acceleration amplitudes become significant, providing insights into conditions that displacement and velocity may not reveal. However, acceleration is less practical for general vibration severity assessment because it does not correlate directly with dynamic stress in the same way velocity does. Instead, it serves as a diagnostic tool for specialized applications where high-frequency phenomena dominate. Engineers often use acceleration data in conjunction with velocity measurements to identify root causes of complex vibration problems and to design targeted corrective actions. Understanding when and how to apply acceleration measurements ensures that high-frequency risks are managed effectively without compromising overall system performance. Amplitude versus frequency for displacement, velocity, and acceleration. The provided diagram illustrates the relationship between amplitude and frequency for displacement, velocity, and acceleration. At low frequencies, displacement exhibits the highest amplitude, making it visually prominent. As frequency increases, displacement amplitude decreases sharply, while acceleration amplitude rises significantly, dominating the high-frequency range. Velocity remains relatively uniform across the spectrum, offering a balanced representation of vibration energy. This graphical comparison highlights why velocity is the preferred parameter for general vibration monitoring, as it avoids the extremes observed in displacement and acceleration. By interpreting this diagram, engineers can better understand how each parameter responds to frequency changes and select the most appropriate measurement technique for their specific application. Uniform weighting and stress correlation. Velocity has become the industry standard for vibration monitoring because it provides uniform weighting across a broad frequency range and correlates directly with dynamic stress levels. This correlation enables accurate prediction of fatigue risks and simplifies the interpretation of vibration data. Industry guidelines and standards often specify velocity-based criteria for assessing vibration severity, ensuring consistency in maintenance practices. By focusing on velocity, engineers can prioritize corrective actions effectively, reduce downtime, and enhance the reliability of critical systems. Its balanced response to frequency variations makes velocity the most practical and reliable parameter for routine monitoring and troubleshooting in diverse industrial environments. Summary and key takeaways of parameter applications. Displacement, velocity, and acceleration each play a unique role in vibration analysis. Displacement is useful for observing low-frequency motion but is unreliable for assessing severity at higher frequencies. Velocity offers a balanced representation across the frequency spectrum and correlates with dynamic stress, making it the preferred metric for general monitoring. Acceleration emphasizes high-frequency components and is valuable for diagnosing specialized issues such as acoustic excitation. By understanding these distinctions, engineers can select the appropriate measurement technique for their application, ensuring accurate assessments and effective corrective actions to maintain system integrity.